do the current slide. And I think we're ready to go. Oh, maybe you can put on the projector today. Now, I'm trying to say this at the beginning of every class. I kind of want to wait until more people show up, but I did that in my last class, and then we took a little break, and I decided to do it after the break. About 2 or 3 people left. 3 people left after the break. During the break, I didn't get to tell them either. So I think I'm going to get it said now, and I may say it again as others come in. This, my biggest and of course best class ever. 18 students, I believe we have, and uno, has turned in the research paper. Only one. Remember, this isn't an optional thing. This is a required grade. Yeah.
I'm almost done with mine.
Okay, good. Please get those in. And I just got a couple of test ones in, so that increases that nicely. But before I got those in, I was missing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 18. So I had fewer in than I had out. So I'm glad that maybe is flipped now. It's 1, 2, 3, 4, 5, 6, 7, 8, yeah. Had 8 in, 10 out. And the second test, haven't gotten any of those in yet, but I know y'all are working on them, so I just picked it up the first time today. All of you do have second test now, right? All right. Now, and we're working on the material that will be on your last test, which will be the final. Okay. Now, this is example 3, top of page. By the way, we're in chapter 10. We did 2 sections in chapter 9, 9.1 and 9.2, and we're on we didn't do 10.1, but we did 10.2 and are on 10.3 right now. So this is in 10.3. Top of page 712, example 3, a curve with 2 tangent lines at a point. Here is the problem, okay? Here is a prolate cycloid, okay, given by these parametric equations. X is equal to 2t minus pi sine t, and y is equal to 2 minus pi cosine t. Okay? Now, this is a portion of the graph. It doesn't give any limits on t here. But as t is coming in, it does this, and back out again. Now, depending on what part of the curve you're on, and this has one point where the curve intersects that point twice. The incoming curve, this one here, its tangent line is going like that, whereas the outgoing, when it crosses that point again, 0, 2 again, this tangent line is like that. Okay? Now, so the curve itself crosses itself at the point 0, 2, shown here. It says find the equations of both tangent lines at that point. Now, just as a reminder, you can look back at Theorem 10.7 to see the parametric form of the derivative, which I think you're used to, and those are in the block. Well, yeah. Okay. So let's go from there. Find the equations of both tangent lines at that point. Now, when they say the equations of the tangent line, that will be an equation. I think they're looking for an equation of y with respect to x. Okay? They're not looking for necessarily the x with respect to t and y with respect to t. Of course, you got to do that, but they're looking for the tangent line, the equation of a tangent line in y's and x's. Y is a function of x. So, where would you begin? How would you begin? If you're looking for, and by the way, this is a point on the tangent line, both of the tangent lines. So we have a point. To give an equation of a tangent line, what else do we need? An equation of a tangent line needs two pieces of information. If you had 2 points, you could come up with the equation of a tangent line, of any line. But if you have 2 points, what else would you need to get an equation of a line? Any line. One other piece of information besides a point. Second? Slope, exactly. And how do we get a slope? What's the, always a pretty good answer in this class? Take a derivative, that's a good one. So we first will take a derivative with respect to x. So let's do this. I'll call it dx dt. I think that would be the safest thing to call it. The reason I say that is x prime might get you, you don't know what you're taking derivative with respect to. So dx dt, what would that be? Not that hard. Help me. First part's really easy. 2, very good. Minus. 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 I put the minus down because that was the minus. Second part of the derivative, dx dt. Second, minus pi cosine t. That pi is just a coefficient, okay? Well, we did that there. Let's do it over here too. dy dt is equal to what? Did you say 2? Pi. Second? Sine t. Excellent. Okay. Because the derivative of cosine is negative sign, so that wipes out the minus sign. There was no t dependence on 2, so that goes to 0. The derivative is 0, and it would be pi sine t. Okay. Now, what is your slope specifically of the all right. Okay. From the formula we did last time, what is the slope dy dt? Pretty reasonable type thing, I think, to ask. So what would be dy dt? That's the slope we're interested in. And here's Connor. Sorry. I said we already know what dy dt is. We want dy dx. That's the slope we're interested in. The derivative we're interested in. Dy dx. Okay? How do we get that? We did this last time. Do you remember how it went? Anybody? Divide them, exactly, just like you would kind of expect to. Dy dt over dx dt, and that would be what? Dy dt is pi sine t over dx dt, which is 2 minus pi cosine t. Now, here we have to pause a moment. And here's the problem. because these intersect at the same points, okay, coming in and going out, we really need to know the t, okay? Now, they did it for us, and that's not very fair, okay? We need to figure out what is the t value on the incoming as opposed to the t value on the outgoing, okay? So let's deal with the incoming first. We know that x is going to be 0 and y is going to be 2, right? Okay? But that's on the incoming side. We have to figure out what the t value is there, okay? So x equals 0, y is equal to 2. So 0 is equal to 2t minus pi sine t, okay? Except, okay? So that says that pi sine t is equal to 2t, right? Okay. And I'm real tempted to write it this way, except that doesn't look all that. Dividing both sides by t and dividing both sides by pi. And that's a rather bizarre thing. That gives me sine t over t is equal to 2 over pi. And that doesn't look like it's very helpful at all, does it? Okay. So that might not be the best way to go. Now, I know they tell you what the tangent lines are, where they are, when t is equal to pi halves. And we can kind of do that by inspection. Let's go back to this form, the first form, that pi, in fact, I think I like this one better. Pi over 2 times sine t is equal to t. That's dividing both sides by 2 alone. Okay? Now, kind of by inspection, you can see when t is equal to pi over 2, then sine is 1, right? Sine of pi over 2 is 1, and then pi halves would be pi halves, right? So it looks pretty obvious that when t is equal to pi halves, you get a point because sine of pi halves is 1. So when t is equal to pi halves, you get one of these points. Now, it seems like there should be an analytical way to come up with it rather than just looking at it and seeing that. But sometimes looking at it is not too bad a thing. Now, let's go and see when t is equal to minus pi halves, sine is minus 1, right? So then it would be minus pi halves is equal to minus pi halves, so there's another one. So t is equal to minus pi halves. And since you see these curves are coming in like that and going out like this one must be, the incoming must be at t equal minus pi halves, the incoming, and the outgoing one must be where t is equal to positive pi halves. Now they don't intersect again. Those are the only two places that are going to cross those 2 points. See, that point, 0, 2. Now that's, to me, is not very satisfying, but at least it gives me that. So, if those are the values, then we plug t equals minus pi halves in up there, and that would give us, and this will be the slope of, I'm going to call it the incoming, okay, and this will be pi, and what sign of negative pi halves? Sign of negative pi halves? Just said it a few minutes ago, seconds ago maybe. Sign of minus pi halves? You got to talk with your trig teachers. Okay. Sign of, huh? No. Sign of 0 is 0. Negative what? Okay. Negative 1 is, yeah, is the answer. Negative 1. So that would be negative pi, okay, over 2 minus, and what is the cosine of negative pi halves? That's the 0. So this will be negative pi over 2, okay? Okay. So it's at the value negative pi over 2, and it also has the value. The slope is negative pi over 2. Okay? So that has, it's at the value t is equal to minus pi halves, but its slope is also negative pi halves. Okay? So now that we know the slope and we know this point, it says find the equation of a tangent line. So it's y minus y1, and your y1 here happens to be 2, is equal to m, which is minus pi halves, times x minus x1, which is just x. Okay? So this would be y is equal to minus pi halves x plus 2. Okay? And sure enough, 2 is the y-intercept, obviously, okay? And the slope here is negative pi halves. Not only is the t negative pi halves, the slope is negative pi halves, which is a bit bizarre, but true. Okay. And this is Davis, right? Right. Now, did you get a copy of the second test? Okay. Everybody here got a second test. Okay. All right.
Did we get the grades for the first test?
Sorry?
The grades for the first test?
I can't hear you one more time.
The grades for the first test.
Okay.
Did we get those?
I think they're on Blackboard.
Oh, they are.
Yeah, I think so. If they're not, let me know, because I tried to put them on. Found out in my Thursday afternoon class, I put one student, got off one when I was putting in the grades, and gave her grade to another student. So let me know if you don't see it. That means I may have errors somewhere. So, yeah. All right. So there we have the equation of the tangent line of the first one. I thought I just had written, there it is. There is the equation of the incoming tangent line, the one with the negative slope. Okay? Now, we use the same formula, but at a different t. This time we're going to use the dy dx at t outgoing. Okay? I'll put OG for outgoing. Okay? And it's going to be the same formula here. It's just we put in a t of pi halves. So that would be pi times sine of pi halves is 1 divided by 2 minus, and cosine of pi halves is 0, so pi over 2. So again, the value is pi halves, the t is pi halves, but also your slope is pi halves. Strange but true, and it is a positive slope, we can tell that. And I think it's pretty obvious when you do this that you have y is equal to minus pi halves x plus 2. No, I'm sorry, positive pi halves, because the slope is positive pi halves. Now, I didn't do the same thing before because, silly me, I didn't realize this is a y-intercept. And if you know the slope is pi halves, then the slope-intercept formula is y is equal to mx plus b, and the b is 2. So it's just pi halves x plus b. Okay? I did extra work last time. I didn't need to. All right. Now, let's see if they came up with a better way than just trial and error in finding those t's. So I think I'll just go to a new slide. Oh, yeah, there it is. Because x equals 0 and y is equal to 2 when t is equal to plus or minus pi halves. No, they didn't. Okay? They just said, voila, here it is. They didn't show you a good way to derive that. Shame on them. Okay? But you can think through it and see that is the case. And for the life of me, that's all they do. They say, because this, okay, you just observe that that is indeed the case. All right. You have dy dx equal negative pi halves when t is equal to negative pi halves, and dy dx is pi halves when t is equal to pi halves. Don't expect that to be the case on any other problem in the world. It might turn out being, but I would say that is rare that when you put the value of t in, that's the value you get for dy dx. Okay? In these particular cases here. Okay. So the two tangent lines are y minus 2 is equal, and they did the same thing I did, minus pi halves x, and y minus 2 is equal to pi halves x. And here's Bailey. There you are. Okay. Now, and that's how they leave the equations of the line, which is what I would not do. I'd say y is equal to negative pi halves x plus 2, and y is equal to positive pi halves x plus 2. But bizarre, they left it in these forms. All right, next we're going to look at arc length. Now, arc length is not, in general, an easy thing to compute. Okay, especially y as a function of x. Remember the arc length formula? Goodness gracious, it was an integral and 1 square root of 1 minus the derivative of the function, or 1 plus the derivative of the function. And it was just rather an awkward thing when your y is a function of x. But when you're in parametric equations, the arc length in parametric form, if a smooth curve C is given by y is equal to f of t, and x equal to f of t, y is equal to g of t, such that C does not intersect itself. Now that last example, it did. So we just can't have it intersecting itself on the interval of interest. Okay? As a less than t, less than or equal to t, less than or equal to b. On that interval, we can't have it intersecting, except possibly at the endpoint. They could be the same point, but that's okay. Okay? Then the arc length of C over the interval is given by, okay? Now, I don't know if you remember your arc length formula before, but before it was 1 plus dy dx squared, okay? dx. Well, if you multiply that by dx dt, then this becomes dx dt squared under the radical. That becomes this, and dx dt squared under the radical, the dx will wipe out, and that would just be dt there, okay, or at least close to it anyway. So anyway, your arc length here is very similar looking form. And if the x dx dt is your L prime of t, and your g, that would be g prime of t, well, guess what? That's not an unusual thing. Now these are the limits on t, so you have to be dealing with dt. So it's the square root of the first derivative squared of that plus the first derivative squared of that. Now, does that kind of make sense? Okay? It almost looks like a distance formula. Okay? Only you're doing the derivatives, not the square of the actual values. But it looks close enough to what we had before. It shouldn't be too hard to remember. Do I try to memorize it? Nah, not really. I'll look it up if I ever need it. So there's your formula. And by the way, they also say, remember it said it can't intersect itself. That also means it can't duplicate itself. You can't have a function going around the same circle time after time after time. This is only going to give you one arc length. So make sure your limits stop before they intersect or repeat themselves. Now in the preceding section you saw, let's see, yeah. If a circle rolls along a line, then a point on its circumference will trace a path called a cycloid. We did that last time. If the circle rolls around the circumference of another circle, then the path of the endpoint is called an epicycloid. It seems like they're skipping something here. No, this is, yeah. This is leading to example 4. Okay? So, here's example 4 then. A circle of radius 1 rolls around a circumference of a larger circle of radius 4 is shown this. So here's a circle of radius 1, diameter 2. And this is a radius of 4, diameter 8. So this circle, beginning at this point right here, here's what it traces. It rolls around the circle, goes up like this, comes in like that, goes like that, goes out and in, this there. I'm sorry. It's going counterclockwise. So it's going here to there, to there, to there, to there. Okay? Now, epicycloid, circle of radius 1 rolls around that, shown in the figure. Epicycloids traced by a point on the circumference of the smaller circle is given by x is equal to 5 cosine t minus cosine phi t. Y is 5 sine t minus sine of phi t. Wow, they look pretty similar in some ways. Find the distance traveled by the point in one complete trip around the larger circle. Okay? Now, you tell me what your first approach to this would be. How would you begin that problem? Any observations? You want the distance traveled by the point. In other words, that distance there, 1 time around. At least an observation. What? Okay, you're going to use the arc length formula. I think that's a great idea. How are you going to do that? Tell me a few steps you're going to need to take to use that arc length formula. Well, let's write it down first. The arc length S is equal to the integral from A to B, okay, of the square root of f prime squared plus g prime squared. Okay, let me be a little more, to me, it'll make more sense. Well, it may not. Y prime squared, yeah, I meant to say x first, but it doesn't really matter. You can put either one of them first. X prime first plus y prime second. Now, here's one problem with this, folks. The prime here is with t, with respect to t, not with respect to x or y. So that prime means, so I probably should have written dx dt squared plus dy dt squared. It's just so much easier to write it that way. Okay? And then that would be, because you're dealing with t's, dt. Okay. All right, so that's a good first observation. You've got to use the arc length formula. Okay? So what are we going to need also in order to use that? Say again?
Balance. Like from A to B. You have to know the balance.
Okay, the bounds. Very good. And that's what I was getting at. I thought that might be your first observation, but not necessarily. So what appears to be the bound? Remember, your parameter is t, which is the argument of the cosines and sines. So what does it seem like t is going from here to there? Recognizing it represents the travel of this point as it goes around there. So t is going from here to there.
4 to 0.
Second?
4 to 0. Are we doing x's and y's?
Okay. I want to know the limits in t. Okay. And let's just call this t equals 0 here. Okay. Now, how far did it go? Okay. That little circle, how did it go to go from that point to that? Okay. Here is this point here. It goes that far here, that far there, and that far there. How far did it go from here to there? What was the revolution of that little circle? Maybe this will help. What is the value here? 4, 0, right? 4 for x, 0 for y. Okay? Your x is 5 cosine t minus sine cosine 5t. Well, it seems like that would be a good place to have t equals 0. So let's see if that works. What is cosine of 0? 1. And 5 times 1 is 5. Minus cosine of 5t. Well, if that was 0, 5t is also 0. Minus cosine of 0 is? Second. Cosine of 0 is 1. 5 minus 1 is 4. So that sure has us starting at the right place. Let's see if the y is at the right place. What's your y value here? 0. Okay. Well, sine of 0 is 0. Is it multiple choice for me? 5 times 0 is 0 minus 5 times 0 is 0. And sine of 0 is 0. Sure enough, it's starting at 0 there. Okay. Now, from this point to that point, your x is going from 0 to 1, and your y is going, x is going from 4 to 0, and your y is going from 0 to 4. Okay? Now, my gut feeling is, and this is just a gut feeling, that's going, the t is looking a lot like a pi halves to. Now, I don't know if that's what it is, but let's see if it is. If, okay, let's put a pi halves in here for the x value. Cosine of pi halves is 0, so this will be 0, and this will be 5 times 5 halves will be 25 halves. What is cosine of 25 halves? You know that? Yes, you do. All of your half pi's for cosine, cosine starts here, 0, 3 has pi, 5 has pi, 7 has, they're all 0. So sure enough, the x looks like it stays at 0. The y, when t is equal to pi halves, what sine of pi halves? 1. 5 times 1 is 5 minus, and sine of 5 times 5 halves. No, I mean 5 times 1 half. Isn't that what we say? Pi halves. 5 times pi halves is 5 pi halves. Okay. Now the sines at, this may be a problem. Because the sine of 5 halves pi, okay, sine of 1 half pi is 1, 3 halves pi is minus 1, 5 halves pi is plus 1 again. So yeah, that would be minus 1, 5 minus 1 is 4. I think we got it. That's going from 0 to pi halves. So if that's the case, then our length thing around here is 0 to 2 pi. But do you really want to do that? Why not?
It seems like
What's that?
It seems like a lot of work.
Okay, well, it might be a little more work, but the thing is, look at this. That arc at least looks the same as that arc, it looks like the same as that arc, looks like the same as that arc, doesn't it? I think it's got to be. So why don't we just do this one? Multiply it by 4. Okay? So that's what I was getting at. That's then going to be our limits. If we do this to be the 4 times the limit, and what was our t going from? 0 to pi halves. And then, what do we need next? X prime. So what is your x prime? Negative 5 times the sine of t plus 5 times the sine of 5t. Is that what you said? Okay. And the y prime would be 5 times the cosine of t minus 5 times the cosine of 5t. Okay. Now we got to square both of those. Old joy. Okay. So x prime squared, right? That's what we need here, is equal to, you tell me, 25 sine squared t. Okay, I think you may be leaving something out, but I'll go and write it down. Plus 25 sine squared of 5t. Is that what you're going to say? Oh, no. I bet you that wasn't what you were going to say. I'm sorry. Okay. You finish what you were saying. Okay. You were doing, foiling it? Okay. This times itself. And this, that would have been a minus 25, wouldn't it? Or not. You tell me. Minus 25. Whoops, I erased more than I wanted to. Okay. Minus 25 times sine of t sine of 5t. Is that right? Yeah. Wait a minute. I put it in the wrong place. Sorry about that. I messed up badly. Okay. Now let's go back up here. That's the one. Wait. I've messed myself up so miserably. I'm not sure which way I'm going now. Let me go back and make sure. That's a plus here. Yeah. That's a plus. Okay. I erased the wrong one. Okay. Now, so it's 25 from that, and then these two would be minus 25 sine t sine 5t. Is that right? And then you do that again, and it's another, so that'll be a minus 50, isn't it? Okay. So we'll make that a 50 sine t, sine 5t. And then the last term is plus 25 sine squared 5t. Is that what I heard you planning to do? You agree with that? All right. Let's do the y prime squared. And what would that be?
Pretty much the same thing.
Second?
Pretty much the same thing.
Okay, 25 sine squared.
Cosine squared.
Oh, cosine squared. I keep my eyes going to the wrong place here. Okay, cosine squared t. Cosine squared t. And that's going to be a minus 50, because you're going to double that, right? 50 cosine t cosine 5t plus 25
The same.
cosine 5 cosine squared 5t. Right? Did I get it right?
The signs are flipped.
I'm sorry?
I think the signs are flipped because y prime is minus 5 cosine 5t instead of plus.
Okay, I can't hear it.
So between the x and the y, the signs are different.
Okay.
If you see what I mean, from x prime to y prime.
Oh, I'm sorry. You're right. But wait. This starts off as a plus and that's a minus. Right?
Oh, no, I take that back. There's a negative in front of the x prime. There's a negative in front of the 5 with x prime. So.
Yeah. Yeah. So they are flipped, but they're one positive and one negative. Right?
Okay, so they are the same thing.
Yes, it winds up being the same thing. Okay. Now we're going to take these two things, the squares, and add them together. And without doing that, writing them out so they take up that much, let's just sort of mentally do it up here. So we're going to have this term added to that term, and what does that give you? 25 sine squared plus 25 cosine squared. Second? Okay, 25 sine squared t plus 25 cosine squared t. And what did you say it gave us? You could factor out a 25, right? Yuck! What does that leave you with? Sine squared t plus cosine squared t, and what's that? 1. So that just gives you a 25. Okay? Since that works so nicely, what would happen if you added this one to that one? Second? Okay, but cosine squared, wait. Yeah, sine squared 5t plus cosine squared 5t is still 1. So that gives you another 25, doesn't it? So that gives us a 50, okay? 25 plus 25, okay? And then you got a 50 of this and a 50 of that. Now, unfortunately, I can't think of anything that's going to simplify, but I think I can write down my sum in there. And I think that's going to be 25 plus 25 is 50 plus, yuck, only it's a minus, okay, okay, 50, this is such a pain in the neck, sine t, sine 5t, minus a 50 cosine t cosine 5t. 50 cosine t, cosine 5t. Okay, all that's under radical, and that's all that we got there, and then we got a dt here. Okay. Now, I know I can factor out a 50, or square root of 50, which is 2 times root 5. So pull that out, and that'll give me 8 root 5 on the outside, right? And then our integral is that, 0 to pi halves of that mess. And that will be square root of 1 minus sine t sine 5t minus cosine t cosine 5t dt. Now, there's got to be something here, and I'm not seeing anything super easy to do. So let's take a look in the book and see if they come up with something reasonable. Okay. Now wait a minute. I did that backwards. It's 5 root 2, not 2 root 5. Sorry about that. The brain is not working today. I think it took the day off. Okay, it's 5 root 2. 5 times 4 is 20 root 2. Now, they didn't pull out the root 2, I did. Okay, and I think I'll live to regret it. Okay, because they say the difference formula for cosine. And frankly, in okay, go to the front inside cover of the book if you've got one. Okay, and I don't see many of you that have one. Okay, and you see this is of the form, okay, none of you have one, do you? This is what they call the product to sum formulas, okay? Where you have sine t, sine 5t, okay? And cosine t, cosine 5t. They just say a difference formula for cosine, which I don't buy. I mean, I don't see why that's the case here. Actually, now I do see it, because it's going to turn out two of the same things. Okay. Basically what you do is look up one of these formulas. The old name for it is the product to sum formula. And they just do it without any explanation of doing it. Let me give this formula to you. It's in the front of the book, if you had a book, which most of you don't seem to. And I just don't have any room to work here. Since they're going to do the problem, let me go to that page. What we've done so far is fine. They left the 2 inside the radical. We took it out. And it says, before applying the theorem 10.8, and by the way, let's go back to 10.8, and it said, such that C does not intersect itself except possibly at the endpoints. But look at that. It says, if a smooth curve C, okay? Guess what? Going from 0 to 2 pi is not a smooth curve, because each of those is not smooth. So therefore we have to do 0 to pi halves and do it 4 times. It wasn't just because it was going to make it easier. Your theorem doesn't apply when you have these non-smooth points in there. Okay? So you have to do it. It's required that you do that 4 times that from 0 to pi halves. So that's the first thing they point out. I just said it makes it so much easier to do. It's essential for you to do that. Okay? So that's why they say that. So you have to do 4 times. Between any 2 points, dx and dy are not simultaneously 0. Okay? They could be 0, but not at the same time. So the portion of the curve generated from t equals 0 to t equal pi halves is smooth. And to find the total distance traveled, you can do the arc length from that portion in the first quadrant, multiply it by 4. And that gives you this, which is exactly what we got. Okay? Now, then you did that, and they found what the first derivative was, just like we did, and the first derivative of the second one, just like we did. And when you do all that together, they skip steps like crazy, but that's exactly what we got, except I took out the root 2. Probably shouldn't have, but I did. Okay? Now, suddenly they say that. So I'm going to try to fill in the blank there for you. Okay? And here, I've got more room to write on this slide. So what we're looking at is sine of t, sine of 5t. Okay? I guess maybe I should make it more generic to begin with. Okay? Let's erase it all. Okay, start over. Sine of u, sine of v. Okay? That's the product. Here is the sum. 1/2, that's why they kept the 2 inside the radical. They were smart. Okay, times cosine of u minus v minus the cosine of u plus v. Okay? And the cosine, u cosine v, is equal to 1/2 cosine u minus v plus cosine u plus v. Okay? Now, that said, let's put in our t and 5t instead of u and v. Okay? So, what we're plugging in is this right here. Sine t sine 5t will be 1/2 times the cosine of u minus v, that would be t minus 5t, would be a minus 4t. Everybody agree? Or not? Okay. Minus the cosine of u plus, and that would be t plus 5t, so that would be 6t. All right. Let's do the cosine of t cosine 5t. That would be 1/2 cosine of minus 4t plus cosine of 6t. What you think? In agreement? Yay or nay? All right. Now, what we're going to do, and you see written in the way they did, they left the root 2 in there. Smart move, because they have a 1/2 in both of those. So the 1/2 is going to wipe out this. So the sine t, sine 5t, now you still got the minus 2 up here, but that 2 goes away. Okay, that's going to be, the 1/2 is going away. cosine negative 4t minus sine cosine of 6t. And we're going, let's factor out the minus signs. Just keep the plus, okay? So that would be that. And then you do, if you factor out the minus sign, this will be cosine 4t with a plus in between, plus cosine 6t. Well, guess what? The cosine 6t's are going to go away. One's plus and one's minus. The cosine 4t, or cosine negative 4t, let's think a minute. What's that thing about even and oddness and sines and cosines? What kind of function is cosine? Even or odd? Anyone recall? Cosine does exactly the same thing on both sides. So the cosine of the minus 4t is the same as cosine of 4t. Sine goes the opposite direction on either side of 0. So that would be an opposite. We're not worried about it. These are all cosines. So that's just going to be cosine 4t. So what we have here is 2 minus, and you had one up there, cosine 4t, another one down here. Those 1/2 went out with these 2's, but now you've got 2 of those again, so it's minus 2 cosine 4t dt. Now, that's a much nicer looking thing here. Still not absolutely certain we can integrate it, or can we? What might you choose to do to integrate that? First thing that comes to mind. Anything. All right. I'd say second thing that comes to mind. Okay. Substitution. That's the first thing that comes to my mind. I'm not sure it's a good thought or not, but at least it's worth a shot. By parts, I don't think it's worth a shot. Okay. Let's hang that one up. Okay. But let's try a substitution. What might you do a substitution? Let's maybe do 2. Let's start with a u equal 4t. That's going to be a pretty simple substitution. Then du is going to be 4 dt, right? So dt will be 1/4 du. Okay? That's just to clear that out of the way. So now our integral would be 20 times the integral, and if u is equal to 4t, t is going from 0 to pi halves, that would be going from 0 to 2 pi. Okay? And that would be the square root of 2 minus 2 cosine u du. Oh, wait. I forgot my 4th. 5. I pulled out a 1/4. Okay? You okay with that? All right. Now, let's do another substitution. Okay? All right. Actually, rather than substitution, I'm going to the back of the book. Okay? Where my integration tables are. Because I have a feeling, rather than the pain of going through this myself, and it's not right at the back of the book where it ought to be, you have to go through all the, wait, I put a marker in it, didn't I? Yeah, integration tables, Appendix B on page A3, as if that helps any. Okay, this is the square root of, see if we can find a trig function. And there's Terrell. Well, I had hoped to find the trig function, but I'm not seeing one with a square root in it. Boy, what a pain. Well, when that fails, which it did miserably, let's go back and see what they do next, okay? Anyway, we got the same thing we did there, so let's erase all the ink on the slide and see what they do next. We got that step. They didn't show you how, but I just did. Okay, Corbin's here, and Terrell is here. All right. And because we have had a few more people come in since the first call roll, let me say this again so I'm sure everybody hears it. Okay. In fact, I may not have said this at the beginning. If my understanding of how the term is ending is right, we have class this week. Already had it Monday, we have it today. And we have it next week, Monday and Wednesday. And then if my memory's right, if my understanding's right, we do have class on Monday of the following week. So in other words, we have, after today, 3 more classes. And then the next Wednesday is your final week type thing. It's not a full week. So what I'm going to be doing is giving you your final exam the Monday, and you turn it in to me either Tuesday, Wednesday, or Thursday. Now, I would say Friday, but I'm not sure we still have, if we open back, you know, if we're going to be here on Friday, if the college is open. But even if the college is open, I won't be here. I've got a treatment that Friday. So I know I won't be in that Friday. But I will be here the following Monday. Now, here's the catch for Monday. Grades have to be due in by noon. So if you are going to turn in something to me that following Monday, okay, I have to have it first thing in the morning. I cannot receive it at 11 o'clock and have grades in by noon. I don't think I can manage that. Not if 15 people were doing it or something like that. So in other words, when I give you the final exam on Monday, that last Monday, then get it into me Tuesday, Wednesday, or Thursday, please. Okay. Or if the school is open and I'm not here, you can slide it under my door on Friday, and that way when I come in Monday morning, I'll have it first thing in the morning. Okay? Does that make sense? Now, research papers. That's a required score. It's not an optional thing. It's not a thing you can drop. It is a required score. And guess what? I've gotten 1 out of the 18 of you has turned in a paper. So please get these in. Okay? Number 2, the first test. Just in the last, well, today, yesterday and today, I received enough to go over half of those in. So I still have several test 1s out, and I haven't received any test 2s back yet, but I'm expecting those soon. So please, folks, don't wait until finals week to say, oh, I got a paper and 3 tests. Yeah, no, that's not going to be the best way to handle your time. So please get the stuff into me sooner rather than later. Okay, that was my commercial break. Let's go on. Okay. All right. Yes?
If you turned in my first test, have you graded it?
Yeah, and the grades should be on Blackboard. They were? Okay. All right. I can't return the paper. You can come see them anytime, but I can't return them to you until I get them all in, because you see then the correct answers will be out there and people, yeah. So that's why I want those in so I can get rid of them. Okay, but I got to get them all in first. So let's see what they did from there. Okay. I took you a little bit of the way. No, what I did. Okay. Now, here's another, that was a difference formula. We got that. This is done by the double angle formula. So again, go back to the front of your book, that first page inside the inside cover, and this will be going from cosine 4t, blah, blah, blah. It's they call it the double angle formula. I'm almost certain that really is the half angle, but let me take a look first. Yes, it's the half angle formula that, and it's cosine, yeah. So 1 minus, so this is going to be the, well, I thought I had it. Well, they don't put it in here as this. They call it the power reducing formula. Okay? Yeah. And let me write that one down for you. Okay, the power reducing formula with a minus sign is this one. Keep losing it. Okay, there it is. Sine squared u is equal to 1 minus cosine 2u over 2, I think it is. Yeah, over 2. Okay. This is the reason they kept the 2 in there, okay, for this very thing here. Well, no, it's not really. Well, it helps. Okay. What we have is a 2 minus cosine 2u, which let's call this, what's in the radical there, 2 times 1 minus cosine 4t. Right? That's what's in the radical there. Okay? Well, this tells us that 1 minus cosine 2u is 2 times sine squared u. So this would be, you had a 2 there, we get another 2 there, and that would be the square root of 4 times sine squared, and take half of that, and that would be 2t. Whew. All right. That is something I can do. That's a square root of 2 perfect squares. So this is 2 times sine of 2t. Okay? So the next step here is, well, I did that. That's what they got here. And then that just becomes, I'm just doing the next step here, 20 times the integral from 0 to pi halves of 2 sine of 2t dt. Right? Okay. I think we can do that integral, can't we? Okay. Goodness, my nose itches. The antiderivative of sine of 2t would be minus cosine of 2t over 2, right? If you're integrating that, okay? You had a 2 out in front, that 2 is going to wipe out that 2, okay? So that gives you 20 times the integral of this dt. Okay? Now wait a minute. I just did the integral. Sorry about that. Getting lost in the sauce here. Okay? That is the integral of this. Okay? The 2's go away. And you evaluate this from 0 to pi halves. Alright. That'd be 20 times, when you put a pi halves in there, what is minus cosine of pi? Cosine of pi is? Help me. Cosine of pi. Anybody? Second? -1. And minus that would be +1. Okay? Minus, from the lower integral, of a minus, which is going to be plus, cosine of 0. What's cosine of 0? 1. Okay? So this is me 20 times 2 equal 40. Can it be? Yes, it can. That is the the loop around that, the total distance traveled is 40. No pi's in it, no radicals in it, just the number 40. Okay? Which is pretty interesting. The bigger circle was a 4. So, well, don't try to read too much into it. So anyway, that's the 40 times the integral from 0 to 2 pi of sine of 2t, which is negative, and they took the 2 outside, so I get 20 cosine 2t, and they just said that's 40, which is fine. Okay. So for the epicycloid shown here, an arc length of 40 seems about right because the circumference of a circle of radius 6 is 2 pi r, which would be 12 pi, which is about 30.7. Why were they estimating with that? Well, if you can imagine, this, remember, was radius 4, and there you have another 2 added to, radius of 4, and then you had a radius of 1 here, but the outside of that would be a diameter, so that would be 6. So if you encircle that with a 6, just circle that would give you 37.7. And the fact that you're only touching that circle a little bit of the time, and you're coming in, whereas the circle is a lot shorter, somewhat shorter, then you expect that to be a little bit greater. And that looks to be a reasonable answer. It's always helpful if something seems reasonable at the end. All right, that took way too long. Now let's look at the area of a surface of revolution, which, if you remember, you did a 2 pi r of your arc length, right? The arc length has a square root in it, pi r squared of it. And so you can use the formula for the area of a surface of revolution in rectangular form to develop a formula for the surface area in parametric form, okay? If a smooth curve, C, catch here, smooth. I did point it out to you before, that's the key here. Smooth curve C, given by x equal f of t, y is equal g of t, does not cross itself, just like before, on an interval a to b. Then the area of revolution, the S, the area, the little s was the arc length, capital S is the surface of revolution, area of that surface, S, of revolution formed by revolving C about the coordinate axes is given by the following. Okay? 2 pi times the integral this was basically your R. Your arc length is how far you are from that. So that's basically come pretty close to being that. And if you're revolving this around the x-axis, then your g of t, I said that wrong. Your g of t is your r. If you're revolving around the x-axis, your g of t is your y. So that's going to be your r then, okay? Your ds, small increment of arc length, is going to be this increment, that ends here, the same arc length you had before. And that's your arc length formula. If you're revolving around the y-axis, then your radius of revolution is going to be your y value, your x value, which is your f of t. So this keeps it all in t's. That's what your variable of integration is the t, and it's already in t's. So you don't have to worry with changing formulas like you used to before. You've already got your x and y as functions of t. So those are pretty straightforward. This thing, 2 pi r, that's the thing, and that's your ds. okay, with a little increment of arc length. So that's your ds. And that works out pretty nicely. Okay? I think there must be, okay, these formulas may be easier to remember if you think of the differential, yeah. Let me see if they say that. Yeah. These formulas may be easier to remember if you think of the differential of the arc length, ds, as being this thing here. That's what I was saying. That's what we were integrating before to get s, right? So that's the differential of the arc length. So you do that. Then the formulas of theorem 10.9 can be written as 2 pi times the integral from a to b of GOT ds. With that being to that, or 2 pi. In other words, revolved around the x-axis is 2 pi y ds. For y is GOT, and around the x-axis, the y-axis, 2 pi x ds. But everything's in terms of t, including the ds's here. So that being the ds, like I was calling x and y, still put that in terms of t. All right. This is example 5, the last example of the thing. Let's see if we can do it, of the section. Let C be an arc of the circle x squared plus y squared equal 9. Okay? It's going to be a circle of radius 3. Okay? So you're going from 3, 0 this way, 3 on x, 0 on y, to 3 over root 2, 3 root 3 over 2. 3 over 2, 3 root 2 over 3 root 3 over 2. All right, that's a rather strange setup, it appears. Now, just thinking here, if that's a 3, then this will be basically your 60-degree line here, because the coordinate for that would be 1/2 root 3 over 2. Okay, if this was a unit circle, so this is a 3 circle. It's 3 halves, 3 root 3 over 2. So that's how far your arc is going. Now, I'm not sure that you need to think in terms of that, but that's just the point. That's where it shows up. Okay. Actually, it seems like to me that would make this to be just a great thing to use polar coordinates on, but we're not there yet. Okay. Or we might not be. Okay. So to find the area of that surface form, you just take that little arc from 3, 0 to that point there, and revolve that around the x-axis. So now you're going to have your y, which is your GOT. That's what we have. Okay. They haven't told us what parameter to use. Now, in an earlier life, you probably could have done this just in x's and y's, but would it have been easy? Kind of doubt. Okay? So now let's do a judicious choice of your variable of integration. Frankly, I would like theta. I bet you they're going to use t. Yep, they're using t. They usually do. All right. Now, can anyone think what would be a parametric equation for x then? Thinking the x is going from 3 to some value up here. Since it's starting at its max, x should probably be the cosine of t, or at least some multiple of that. That would give you a value of 1 when t is equal to 0. To make it 3, just multiply by that. Okay? Y then would be equal to, you're starting at 0 and going to some higher value here, but it's everything multiplied by 3. So let that be 3 sine t. Okay? Now, what are your t's going from? I've already sort of hinted it's starting at 0. So your t will be going from 0 to, what value gives you this? The x going to 1/2 or 3/2, starting at 3 going that way. I'm pretty sure that's pi thirds, right? And the y is going, the sign is going from 0 to 1/2. Wait. No, root 3 over 2. The y is going from 0 to 2. So yeah, I believe that works. T is going from T is an element of that, going from there. Okay? So, with that in mind, what else do we need to do? We need to do your dx dt's, the dy dt, and then do all that other mess. Okay? So, dx dt is what? You tell me. Anybody? Anyone? Help me. What's your dx dt? Anybody? X is 3 cosine t. Dx dt would be? It's not that hard. Okay, I heard a 3 and I heard a sine t. Is that your final answer? Negative. Very good. What's your dy dt? Three cosine t, and that one is positive. Okay? But we're going to square both of them, aren't we? From here. Okay? So we're going to square that. So dx dt squared. In fact, why don't, yeah, well, let's just do it down here. Would be what? Not that hard either. Help me. 9 sine squared t, right? And dy dt squared will be 9 cosine squared t, right? And then the sum of those together will be yeah. Plus cosine squared would be 1. So that would just be square root of 9, which would be 3. Square root of 9 equal 3, because we're taking the square root of them, right? So this part would be 3, okay? That's it. That's that part, okay? The first parts are 2 pi. Now, remember, we're going from 0 to pi thirds. And which are we revolving around? Around the x-axis. So it's the y that's going around here, and the y is your this one. So let's write down our surface area. Find the area of the surface. S is equal to 2 pi times the integral from 0 to pi thirds. Your g of t, your y value, is 3 sine t, okay, and then your ds is this thing up here. We calculated that to be 3, okay, times another 3 dt. Well, let's take these 3's, that 9, multiply it by 2, and that's going to be our 18 pi times the integral from 0 to pi thirds of what? Sine t dt, right? Wow, that simplified, didn't it? That'd be 18 pi. And what's the antiderivative of sine t? Second? Yeah. Nope. Negatives, right? Okay. Negative cosine t. Evaluated from 0 to pi thirds. So that's 18 pi. Okay. Now, what is the cosine of minus of pi thirds? Okay. Isn't cosine your x value? Okay. And that would then be 3 over 2. Okay. So that part would be 3, okay, a minus 3 over 2. Remember, that's a minus there. Okay. Then a minus, that minus is going to be plus, and what's cosine of 0? Okay, in this case, wait. I'm sorry. You're right, it's 1/2. We're not on this circle anymore, but I was showing you that. Okay. Okay, so it's a minus 1/2 plus 1. So guess what? That's going to be 1/2. So that's 9 pi. That is our answer. It's also their answer. Okay. When you can represent C parametrically, okay, by the equations x equal 3 cosine t, y is equal to 3 sine t, when t going from 0 to pi halves. Notice you can determine the interval by observing t is equal to 0, x equal 3, t equal to pi halves, x equal to 3 halves. Okay? I think we did all that. On that interval, c is smooth, y is non-negative, and you can apply the theorem to obtain the surface area, and this is what it would be. The surface area is at 2 pi, that's the interval from 0 to 3 halves, that's what the t is going from. Your y value, which is revolving around the x-axis, is 3 sine t, up there, times the square root of all that, and we did this before, and this would be 9 sine squared plus 9 cosine squared, that would be 9, square root of 9 is 3, there's a 3, take those 3's on the outside, and here's Justin on the inside. Okay. All right. Does anyone else come in since we called it over? Okay. Again, let me just say this again so everybody has heard it at least once, most of you more than once. Please get your, and Justin's already turned in the paper, so that's great. Papers in sooner rather than later. Get your first test in sooner rather than later. Get your second test in as soon as you can, because your third test, the final exam, will be coming to you on that last Monday, and you've only got a few days to work on it. I'll try to make it a little shorter than the other tests have been, but that's going to be tough because 10 questions doesn't seem that bad, but hopefully you'll be able to get them done. Okay. So anyway, we did all this, and they pulled out the, why they did that, they pulled out the 6 here, but left the 3 inside there. Seems like a dumb move to me. And, well, they haven't got there yet. I guess they got that 3, so pull that out again, and that would be a minus 18 cosine t evaluated from 0 to 3 halves, 3 pi thirds, and that would be minus 18 pi times 1/2 minus 1, which is, turns out being a negative 1/2, so that gives you a 9 pi. I think they sort of went around their elbow to get to the ear, but they got there. Okay. That ends the section. Any questions on that before I did it off pretty quickly? Any questions? Okay. Homework exercises here. Do either 5 or 7. They're both at Calc Chat. 5's at Calc View. Do any of the odds 9 through 18. They're all at Calc Chat. 13's at Calc View. Do either 19 or 21. They're both at Calc Chat. 19's at Calc View. Do either 23 or 25. They're both at Calc Chat, neither at Calc View. Do either 27 or 29. They're both at, or both if you choose, both a calc chat. 29 is a calc view. Do 31, it's a calc chat. Do any of the odds 33 to 41, they're all at calc chat. 35 is a calc view. Do any of the odds 43 to 47, they're all at calc chat. 43 is a calc view. Do any of the odds 49 to 53, they're all at calc chat. 51 is a calc view. Do either 55 or 57 or both if you choose, that's up to you. Then you choose which ones you want to do next. I'd say any of the odds 59, either 59 or 61, or both if you choose. They're both at calc chat. Then I would do either 63, any of the odds 63 to 67. They're all at calc chat. 65 is at calc view. Then either 69 or 71. They're both at calc chat. 73 is sort of a writing one, so if you want to look at that, you can. 75 is sort of a sketching the graph one. You can do that if you'd like. 77 is integration by substitution, which probably is not bad to review. 79 is one given there. You certainly could do that one. All these are at calc chat. Do any of the odds 81 to 85, they're all at calc chat. Okay, none at calc view. Do 87 is a calc chat. 89 is a calc chat. And any of the odds 91 to 95, they're all at calc chat. True false 97 and or 99, they should be at calc chat as well. Okay, now what I was trying to recall, if the course description called for 10.4, for some reason I had marked in my book that we would be doing 10.4, so I guess the course description called for that. Usually I try to avoid this one, but let's see about it. Okay, how are we doing on time? Actually, yeah, we go until, yeah, we got plenty of time, right? Yeah, seems like we've been going longer than what we've been. Okay, I think I'm just hungry. I don't know why. Okay, let's close this and go. Ooh, where is my? For some reason, my removable disk wasn't showing up anymore. All right, get that back again, and I don't know why it disappeared. 10.4, good buddy. Okay. Goodness, this is taking forever. This morning, the PowerPoints just went on and on and on. I did it in 40 minutes between classes, and it took too much of that 40 minutes. It wasn't that much. Ah, here we go. All right, let's go to current slide. Okay, we're back in chapter 10 again. Now we're at 10.4, polar coordinates and polar graphs. First objective, understand the polar coordinate system. Have y'all dealt with it before? Much? Any? No. Okay. Rewrite rectangular coordinates and equations in polar form and vice versa. I think you'll find that a lot easier to do than you might have thought. Sketch graphs of an equation given in polar form. That's a little bit new way of thinking, but it's still not too bad. Finding the slope of a tangent line to a polar graph. And first, that might seem a little daunting until you realize you're just using parametric equations. We already know how to do that. And we'll identify several types of spectral polar graphs. So let's first start with polar coordinates. So far, we have been representing graphs as collections on the Cartesian coordinate plane as xy, on the rectangular coordinate system. And we're used to that, right? Well, guess what? Some things set themselves up for much easier to be done in other orientations, okay? And that's what we're going to talk about, polar coordinates. Corresponding equations of these graphs have been either rectangular or parametric forms, okay? In this section, we'll study a coordinate system called polar coordinate system. Maybe that's why they call it polar coordinate. Yeah, well, never mind. Okay. To form the polar coordinate system in a plane, we fix a point, the origin, pretty much the same origin as we used before, okay, called the pole or the origin. We construct from that point an initial ray, the polar axis. Not too new here either, as shown here. And then every point in the plane is represented by an ordered pair, but not of x and y, but by r, which is the distance from the origin, and theta, which is the angle that's been rotated in the counterclockwise direction from your polar axis. Okay? The polar axis is always assumed to be, say always, just about always assumed to be the positive x-axis. And what angle do you subtend when you go from there up to the point P? Okay, the horizontal plane from the origin up to that point P. R is the distance that you are from the origin, the pole, and the angle is how far you rotate it in degrees from that pole. Okay? The directed angle. So it's a pretty simple system. Okay? Each point P in the plane can be assigned a polar coordinate, r theta, where r is the directed distance from the origin to that point, and theta is the directed angle, counterclockwise from the polar axis to the segment OP. So here are 3 points on polar coordinate system. Okay? Sort of get used to this bullseye type figure because that's what we're going to be using. Okay? They've shown a radius of 1, 2, and 3 all around it. Okay? Everywhere on that circle, the R value is 2. Everywhere on this one, the R value 1. Everywhere on that circle, R value is 3. And you can imagine a 0.5 would be on that circle, a 1.5 would be on this one, a 2.1 would be some circle just beyond that one. So those are your R values. Now, your angles in the first quadrant would be something between 0 and pi halves. And we use radian measures. Don't start reverting back to degrees. Stay with radians, okay? And this would be pi thirds. If that angle is pi thirds, yeah, then that would be 2 common pi thirds, okay? Now, if you happen to drop below this, that would be on the third circle, 3 comma negative pi 6, because you're in that direction. Now, here's the problem with polar coordinates. In rectangular coordinates, that point has one and only one xy value. All you got. This point right here, you could have said that is 3 times 11/6 pi. A different theta value for the same point. Same R value, different theta value. They made an error here. Anyone see it? Negative sign should not be there. It should be 3 11/6 pi. Negative 11/6 pi would be up here. That wouldn't be this point. So that negative should, well, I probably should do it in red, but I'll do it in darker color. That should be a plus, not a minus. Okay? So, you have an infinite number of values you can give to any point there. And we haven't even talked about negative r's, so we won't mess with that at all. But there's way too many values to do. So we'll just leave that for now. Notice that in this system it is convenient to locate points with respect to a grid of concentric circles intersected by radial lines through the pole. With rectangular coordinates, each point xy has a unique representation not true with polar, like I just pointed out. For instance, the coordinates r theta and r of 2 pi plus theta, of course, are the same because 2 pi plus theta is just one circle around 2 theta. Okay, so you're back at the same position. They're the same points. Okay. Also, because r is a directed distance, the coordinates r theta and negative r theta plus pi, they're the same point. That's why I said we haven't even talked about negative r yet. A negative r would send you in the opposite direction for the angle theta that you're looking at. You know, so that's a bit bizarre. Okay. In general, the point r theta can be written as r theta is equal to r comma theta plus 2n pi, and r theta could also be written as negative r comma theta plus 2n plus 1 pi. In other words, your odd number pi's multiples, where this is the even number pi. Where n is any integer, moreover the pole is represented by 0 theta, where theta is any angle. So not even the origin is unique, because doesn't matter what angle you put there, if the radius is 0, you're on the origin. So there's a couple little squirrely things about polar coordinates, but in some problems, it's the way to go. Okay? Let's see. And by the way, the mathematician credited with first using polar coordinates was good old James Bernoulli, okay, who introduced them in 1691. There's some evidence that it may have been Isaac Newton who first used them, but we just don't have record of that. We have some evidence that he may have, but boy, Newton did so much. It's amazing. And we've talked about the Bernoulli family, haven't we, or did we? We did, okay, because I teach several math classes, and I don't remember which ones talked about it this time. So now let's look at coordinate conversions, and I think you'll find these are way easier than you may have thought. To establish a relationship between the polar and rectangular coordinates, let's let the polar axis coincide with the positive x-axis. That's what it said. It's usually going to be the case. The pole being the origin and the polar axis the positive x-axis. Then we'll superimpose onto the xy coordinate system the polar coordinate system, or onto the polar coordinate system the xy, but with the pole being the origin and the polar axis being the positive x-axis. Okay? That's what we usually did in trig and everything else anyway, so it's nothing unfamiliar. Now let's notice a few things. These are key. With this in play, this point up here will be some value of x, some value for y. Okay? It will be some value r and some angle theta. Okay? And from geometry, trig, and lots of things, we already know these relationships. That x squared plus y squared is equal to r squared. Good old Pythagorean theorem still works here. So r squared is equal to x squared plus y squared. Right there's your relationship between r and x and y. One of them. Okay? Something else we know from trig, the angle theta, let's take the sine of that angle theta, is the opposite side y over the hypotenuse r. So sine of theta is equal to y over r. That means y is equal to r sine theta. There is how you get from polar coordinates to rectangular coordinates. And the cosine of theta is equal to x, the adjacent side over the hypotenuse, and that would be x over r. So therefore, x is equal to r times the cosine theta. There we have another relationship, okay? And if you needed it, tangent theta is equal to y over x. Not sure you need that one. Well, it is going to be useful later. Many times useful later. Okay? And basically, all those work even if your r's are negatives. You're not used to having a negative r, but they still will work. Okay? So that's how we get back and forth. This is how we get from rectangular coordinates to polar coordinates. This is the first way. The second way is this one. This enables us to get from rectangular coordinates to polar. This gives you your r. This gives you your theta. To go the other way, to get from polar to rectangular, multiply both sides by r. X is equal to r cosine theta. Y is equal to r sine theta. Just plug in your r thetas, you can get your x. Plug in your r theta, you can get your y. So it's really pretty easy to go back and forth. So here's the theorem, coordinate conversion. The polar coordinates r theta of the point are related to the rectangular coordinates x, y of that same point as follows. X is equal, this is polar to rectangular. If you know polar, here's how you get rectangular. X is equal to r cosine theta, y is equal to r sine theta, just like I showed you before. And if you're going the other way, I usually do this on top of r theta, not theta r, but it doesn't matter. Tangent theta is equal to y over x, r squared is equal to x squared plus y squared. If you know your x and y, you can get the others. Now, you might say, but that's tangent theta, not theta. Well, all you do is do an inverse tangent of this. So theta is equal to inverse tangent y over x, and r is equal to the square root of x squared plus y. Okay. Either way you want to do it. Okay? So, here is example 1. For the point, r theta is equal to 2 pi. Now, it would be easy enough to plot that, and it's a really easy one to do, but don't plot it. Let's actually calculate it. What are the xy points corresponding to that? Well, I hate that they've already written it for you, but they have. Okay. What is your x that we just had? What was x? R cosine theta. Okay. Plug in. R is equal to 2. Theta is equal to pi. What's 2 times, what's the cosine of pi? What's the cosine of pi? Anybody know? A little louder? -1, exactly. And 2 times that would be -2. So your x is going to be -2. 2 times cosine pi, which is -2. And what's your y? What's your y? R sine theta. And your r is 2. Your theta is pi. What is sine of pi? Say again. A little louder. 0? Absolutely. So your y is 0. So the point is -2, 0. Okay? Of course that is. If you plot that, usually you plot your theta first. Okay? And theta pi is all the way over here, right? Halfway around the circle. So the circle is 2 pi. You go out 2 units. -2, 0. Okay. Good deal. So the rectangular coordinate is -2, 0, as we just saw. All right, here's another. For the point r theta is √3 pi 6. What is x value? What's the formula? Let me cover this. Is what? Is √3, that's the r, times the cosine of pi 6. And what's the cosine of pi 6? Okay. Okay. Multiple choice for me, right? Okay. Second, root 3 over 2. Cosine of pi 6 is root 3 over 2, okay? Times root 3 would be 3 halves. Okay? And what's your y value? R sine theta, which is root 3 times what's the sine of pi 6? Second? 1/2. Okay? So it's root 3 times 1/2, which is root 3 half over 2. Okay? So the x value would be 3 halves, y value root 3 over 2. Okay? So you would be here on the circle that's root 3 in radius, pi 6 up here. Yeah, good enough. First quadrant, not too far up. Okay. See, so the rectangular coordinates is 3 halves root 3 over 2. Okay? And here those are. The first one here, -2, 0, because you went r of 2 and theta pi. Pi halves pi. Okay? And the second one for r, your r is root 3. Root 3 is something a little less than 2. So you go up here and you go up pi 6, which is 30 degrees here, and that would be 3 halves for that one, because it's root 3 times root 3 over 2, which is 3 halves, and then 3 halves times root 3 times 1/2. Okay. Now, that was example 1. Okay? They're skipping example 2. Okay, how are we doing? Good. Okay. So let's go back and do example 2. All right. Do we need a break? Okay, I'm all in favor. So let's take a quick break and we'll get to example 2 when we get back. Okay, we finished example 1. Let's do example 2. Okay? We don't have this on the slide set, so let's do it ourselves. Now, what if you have an XY point, and I'm just going to do it. I was going to pull up a graph, but it's going to take too long to go back and forth. XY point, and we don't even have to draw it, -1, 1. Okay? Well, -1 is going to be over here. 1's going to be up here. So here's your point, -1, 1. And they call it a second quadrant point. Sure enough, it's true. Okay? That is your rectangular coordinates of that point. Okay? It says here, for that point, you find the polar coordinates. It takes them a while to say that. What are the polar coordinates? How do you find them? Anybody? Okay. Which you want to go for first? What are your two polar coordinates? Your XY your rectangular coordinates are X and Y. There they are. What are your polar coordinates? What are their names? It's been a long time, huh? There they are. Previous problem. R and theta. What in the world is R in terms of the rectangular coordinates? Or what is R anyway, whether that was there or not? What would be your R? Second? I can't. It's like a radius, okay? It would be the radius or the distance from the pole to the point. And how will you determine that distance? This is your R. So how would you determine that in terms of r of x and y? Second? Theta is 0. Theta is 0 here on the polar axis. That's where it's 0. That's certainly not 0. Okay? But how about the r? Second? Square root of 2, exactly. It's a good old Pythagorean theorem, the square root of x squared plus y squared. That's r squared. I mean, that's r. So it's the square root of 2 is r. Perfect. Now what's your theta? Not 0, by the way. Okay? Do you remember the kind of the formula for it? You're trying to get theta. One of the trig functions gave you a relationship between theta, x, and y alone. Remember which one? X being the adjacent side, y being the opposite side. Okay, Pythagorean theorem gave you the r. We got that already. That was the square root of 1 squared plus 1 squared. Or a minus 1 squared plus 1 squared, which is still 1 plus 1 is 2, square root of 2. The question is, what is the theta? Well, angle theta here, how does that relate to your x and y values? Where x is the related to the adjacent side and y is related to the opposite side. What trig function relates your opposite to adjacent? I need to talk with your trig teacher because I know who he was. Me. Huh? Okay. Yeah, but we're not dealing with hypotenuse. We're doing just the adjacent and opposite. Which is opposite over adjacent? Remember, taking oats away? Tangent, exactly. The tangent of the angle theta, this theta here, is equal to y over x, opposite over adjacent. Okay? With a problem. Okay? This is only good from minus pi halves to pi halves. We're over here. So when you do this, you're going to get an angle somewhere in between these two. But what you do, the angle you're going to get is this one. Add pi to it, and that's going to give you the angle theta. Okay? So basically you do theta is equal to your y, which is 1. I'm sorry. Back off just a second. The inverse tangent of y, which is 1 over negative 1, which is inverse tangent. Goodness gracious, I can't write today. Of negative 1. What's the inverse tangent of negative 1? That is one ugly tangent, isn't it? Okay. They both are. What's the inverse tangent of negative 1? What angle, when you take a tangent of it, do you get minus 1? Second? No, we're looking for an angle, theta, not a trig function. An angle theta, if you take its tangent, you get a negative 1. I don't know if it's helpful to you to think, what does a tangent function look like? I'm going to draw it here. Okay? Shouldn't do it on the same graph. But these are the asymptotes, minus pi halves to pi halves. Right? Can't touch either one of those. Right? It's going to negative infinity here. It's going to positive infinity there. Okay? Now, places that we know 0 at 0, this is pi halves. At pi fourths, it's 1. And at minus pi fourths, it's minus 1. Remember that? So therefore, the angle whose tangent is negative 1 is minus pi fourths. Well, that's someone down here, minus pi fourths. We're over here. So what do we do to get over there? What's the angle measurement of a straight line? How far did I travel? 180 degrees, which is how many radians? Okay. Hint, how many radians is all the way around the circle? How many radians is all the way around the circle? 2 pi. So halfway around the circle would be pi. Add pi to negative. We said that was negative pi fourths. So pi plus negative pi fourths will be what? How many fourths pi is pi? Okay, now pi fourths is 4 pi over 4, isn't it? 4 over 4 is 1. Right? Okay. 4 pi minus pi is 3 pi over 4. Okay? Now, there's your angle. Your angle theta is 3 pi over 4. So your polar coordinates are r root 2 theta 3 pi over 4. There are the polar coordinates for this point here. So that would be, put those in the bank right here. If you're in polar coordinates, this would be root 2 3 pi over 4, 3/4 pi. And you know that's true, don't you? This is 1/4 pi, 2/4 pi, 3/4 pi. You could have just picked that up almost from looking at it, okay? And then the radius is, make sense? Okay. Now, that's the A part. Hopefully the B part won't be, hopefully it'll be a lot easier for y'all to pick up on. Okay? Where is it? What is the B part? Oh, here it is. The point XY is 0, 2. So let's try to write it without. XY is equal to 0, 2. Okay? We want the polar coordinates for that point. What are the two polar coordinates? R and theta. And what is R? I don't think so. If R were 0, you'd be at the origin. Okay? It's 2. It's got to be 2 because it's the square root of x squared plus y squared, which is the square root of 0 squared plus 2 squared, which is the square root of 4, which is 2. Okay? Long way around is 2. What's your theta? Second? No, this is tough, I think. It's not 0. If this would have been 2, 0, you'd have been right on the money. It would have been 0. Theta would be 0. But at 0, 2, we have a problem, Houston, because theta is the inverse tangent of y over x, opposite over adjacent. And what would that be here? Inverse tangent of 2 over 0. Do any bells go off? You can't do it, okay? Or, the other way to look at it, this is a vertical asymptote. And where does a tangent have a vertical asymptote? It has 2 of them. Say again? Not at pi. Pi halves. Pi halves and also negative pi halves. Remember, we just drew that. Vertical asymptote. Negative pi halves and pi halves. Since you're on 2, you're up there, that's going to be at pi halves. See, if I had drawn this one, I think this should have been very easy. So therefore, your theta is pi halves. Okay? So your polar coordinates for this would be r theta equal 2, pi halves. Okay. Perfect. And that's why I said I refrained from graphing it, because if you graph the point, there's 1, 2, 1, 2, 1, 2, 1, 2. 0, 2 would be 0, 2. There's your point right there. Pretty obvious that theta is equal to pi halves, isn't it? Same thing as we did for trig. And it's pretty obvious, too, that the radius, the distance between that point and there, r is equal to 2. So if we had applied it that one, you could have almost written it down without using a formula at all. It would have been obvious it's 2 pi halves. Okay? Good deal. Now, let's go to polar graphs. That means very cold graphs. No, that's not what it means. Okay. What we mean here, they jump right into it. Okay, we'll describe the graph of each polar equation. Confirm each description by converting to a rectangular equation. Okay? So r is equal to 2. First, you tell me what that represents. R is equal to 2. Say again? The radius is 2. Is that what you said? Okay. Yeah, the radius is 2. Radius of what? Circle. You can let theta be anything in the world. So radius of 2 would be 2 units from the origin. Every point 2 units from the origin. Guess what that describes? A circle of radius 2, okay? Centered about the origin. Okay, so that's a description of the graph. That's a circle. Remember when we did our first thing? The radius 1, radius 2, radius of 3. That's your radius of 2. That circle, that would be right there. Okay? Now, confirm each description by converting to rectangular equation. Well, what is r in terms of rectangular? Okay. What is x in terms of r? Okay. X is equal to what was our formula for x when we were converting back and forth? Second? R cosine theta. And y is? R sine theta. Okay? Now, what is r in terms of x's and y's? Is what? R in terms of x's and y. The word Pythagoras ring a bell. X squared plus y squared. But let's make this r squared and make it a little easier, which would be 2 squared. So this is equal to 4. Okay? Isn't that a rectangular equation? X squared plus y squared equals 4? How would you describe what that graphs? You not run into this graph before? As long as these coefficients are the same, that forms a circle of radius 2. X squared plus y squared equals r squared. That's a circle of radius 2. There is your converting into a rectangular equation. We really didn't need the top part. I started doing it that way. I thought much easier to do it this way. Okay, theta equal pi thirds. You first describe to me the graph of that polar equation. What does it mean for theta to be pi thirds? Where do you start your theta? Horizontal x-axis, right? And when you say theta equal pi thirds, what have you done to it? You rotated it about the origin. How far? Pi thirds. And how far is pi thirds? 2/3 to 90. Right? Because 90 is pi halves. And that would be 2/3 of the way there. In other words, 60 degrees. Right? You rotated 60 degrees. So what have you got here? You've got a straight line that's going from the origin that way as long as you can go. So that would be a straight line. Okay? That's the description of it. Not a line. It's a ray starting at the origin going that direction. Okay? Now, if you included r's of negatives, then you could go straight line period. But we won't do that yet. Okay? So that would be a ray from the origin through an angle of pi thirds. Keeps going forever. So we need to convert that to a rectangular equation. Okay? Now, see, it really doesn't matter what x or y value you have. So those two and even that equation really won't be all that useful to you. Let's do the one other equation that might be, I'm not sure it would be either. Okay. Well, what does this tell? Okay. What's your equation that gives you relationship between theta and x and y? Do you remember it? Okay. So I'm going to write it in tangent. Tangent of theta is equal to which? Y over x. Okay? Or y is equal to tangent theta times x. I say x and write y. There's something not clicking very well. Okay? Times x. Okay? Now, What is your theta? Pi thirds, right? So we got y is equal to the tangent of pi thirds times x. Okay? Now what is tangent of pi thirds? Remember on your unit circle? Ooh, that's an ugly one. Pi thirds is somewhere up here. Remember what the coordinates were? The x coordinate is, this is unit circle 1, 1, negative 1, negative 1. This looks like to be about okay, you don't trust my drawing, I understand that, okay? It's 1/2. Okay? And what's the y coordinate for it? Anyone remember? If this radius is 1, which it is, and this is 1/2 down here, you remember what this value is? Root 3 over 2. Okay, now, some of you were in my trig class, and that you're not remembering this. Okay? Weren't you? No, okay, sorry. Okay. But, here is a fairly easy to remember. Remember what our favorite angles are? Pi 6, pi fourths, pi thirds, and pi halves. And 0, too. Okay, let's do the coordinates for that. 1, 0. Okay, this one was something else. That we already labeled. And this one, anyone remember what these are? That's pretty easy. 0, 1. Okay, here is the easy little way to do this. Let's start with the y coordinate. Square root of 0 over 2, which is, of course, 0. Square root of 1 over 2, which is 1/2. Square root of 2 over 2. Square root of 3 over 2. And this is square root of 4 over 2, but square root of 4 is 2, and 2 over 2 is 1. Right? Do the same thing in the reverse direction here. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2, which is 1. 2 over 2, 1. These ought to be pretty easy to remember. Okay? And this is pi 6, pi fourths, pi thirds, and pi halves. Okay? Those should come pretty easily. So what is tangent of pi thirds? Now that you've got the coordinates, what is tangent? In general, what is tangent? Taking oats away. Opposite over adjacent, which is your opposite side is your y, your adjacent side is the x, so it's y over x. And when you're at pi thirds, which is what we are right here, what's your y over x? Root 3. That's it. So y is equal to root 3x. There's the equation of that line that goes not just to the unit circle, but goes forever up there. Its y-intercept is 0, 0. That's why you don't have a constant on it. Its slope is root 3. Goes up root 3 for every one it goes up. Does that make sense? Okay? All right. How about this one? R is equal to secant theta. R is equal to secant theta. It says describe the graph of that polar equation. Okay? Now, this actually the graph of it is harder to do. The other two you could just think about what the graph was. This one you're going to have to do a little bit of work to do the graph. Okay? And on this one, let's take these points that we have right here, okay? Now remember what the secant is. Someone tell me what secant is in terms of the ratios. What is secant? Or maybe with an identity. What other trig function relates to secant? I need to talk to some trig teachers. What is secant? Please, somebody. Reciprocal identity. What is secant? Second? Yeah, it's exactly 1 over cosine. Okay, and what is cosine? In terms of your call another hen. Does that make any sense to you at all? Cosine is adjacent over hypotenuse. Adjacent is your x value. So the cosine, if cosine is adjacent over hypotenuse, call another hen, then the secant is going to be hypotenuse over adjacent, right? The reciprocal of cosine. What's your hypotenuse? Okay. In terms of r and theta, this will be r over adjacent side is x. So we're sort of mixing them up here. Okay? So let's get that down. R is equal to r over x. Okay? Oh, wait. I'm sorry. We were graphing it first. I'm already doing the thing. It's going to be much easier to do than what I was just doing there. So we got r over x, or h over a. Okay? So let's start with theta equals 0. Does anyone remember what? Well, yeah. This will give it to us right here. When theta is equal to 0, what is cosine theta? Theta equals 0. What's cosine theta? I think we've done it about 3 or 4 times today. What's cosine of 0? 1. Very good. And 1 over 1 is 1. So when theta equals 0, okay, I'm going to wipe out. Oh, no, that's not what I meant to do. But it's okay. All right. All right. Okay. When theta equals 0, your r is equal to 1. Okay? Now when theta equal, let's do an easy one, pi halves. Okay? So this will be theta equal pi halves, pi 6. Let's do pi 6. Theta equal pi 6, this will be 1 over cosine of pi 6. Now erase what I meant to keep. Does anyone remember what cosine of pi 6 was? Exactly. Okay? So 1 over that would be 3 over 2, 2 over the square root of 3. If you got a calculator, punch it in. 2 divided by root 3. Anyone? Okay. So when theta is equal to pi 6, we're here somewhere. What's 2 over root 3? Second? 1.1. Let's just say it's, I don't know, here's 1 and 0.1. Something about like that, okay? Now let's do secant of pi fourths. Anyone remember that's 1 over cosine pi fourths? Does anyone remember what pi fourths is? Square root of 2 over 2. Do that one. That's about 1.7. Oh yeah, but only you do 2 over root 2, or root 2. It's just root 2, which is 1.414. And now we're about here, so I think we're somewhere about there. Okay, and then let's do secant of pi thirds, which is 1 over cosine pi thirds, and that would be, so that would be a 2. So when you're up here, you're around a 2. This is looking suspicious, isn't it? Okay, and when you're at pi halves, what is secant of pi halves? What's cosine of pi halves? Cosine of pi. 0. And what's 1 over 0? Absolutely undefined, right? So you can't go there, and it's never going to be. So I think what that means here is the graph of that function. It can't ever get there. The higher you go in the angle, the further out you go, and you're never going to reach pi halves. Never. Okay? Go way up there, you're awfully close to pi halves, but not there. I think this is a vertical line at x equal 1. That's a little bit harder to justify. It's not obvious that's what it is, but that's what I think it is. Okay? Now it's going to be really easy to come up with a rectangular equation. Don't you think? Oops. Okay. Sorry about that. With a rectangular equation, where is my pen? Okay, there it is. So r is equal to 1 over cosine theta. Guess what we can move? Don't we want to get all the... You tell me something that you think we could do to that to simplify. What don't you like about it? That denominator. We don't like denominators, do we? That means fractions. We don't like fractions. Okay? So why don't we multiply both sides by cosine theta? Okay? So, what do we have here? 1 is equal to r cosine theta. Does anyone remember what r cosine theta is? X. X equal 1. And wasn't that what I just described? If this is your rectangular coordinate system, x equal 1. I didn't do the lower part, but you could have. That's it. We guessed right. Vertical line, x equal 1. See how that works? All right. I think that's all we have time for, isn't it? Okay, before we go, let's see, what's the next slide? Oh, let's just show this quickly, because they did it here. What is r equal to? That's where your concentric circle at 2. R is 2 everywhere on that circle, okay? And what would that be in a rectangular equation? X squared plus y squared equal 2 squared, or x squared plus y squared equal 4. And we got that because r was the square root of x squared plus y squared, right? And if that's equal to 2, then square both sides, you get x squared plus y squared equal 4. Okay? Now the next one, the polar equation theta equal pi thirds, that's that line that goes up there through pi thirds, no matter what your r is. Okay? So that's a straight line going through the origin, The slope of that line is root 3 over 2, right? I'm sorry, root 3. Yeah, I'm sorry. The slope of the line is y over x, which is root 3. We did that. And so that's y is equal to root 3x. Perfect there. Okay, this one, that one took a little bit more effort, but actually they started with the equation, and that was much easier to do this way. Multiply both sides by cosine squared, r squared, cosine theta, r cosine theta is equal to 1. That's x equal 1. Draw your line, x equal 1. There it is. So it was far better to draw it first and then plot it later, okay? Now, that's the next slide. I need to find where, oh, there it is. There it is. Okay. No, it isn't. I don't know. I don't see this slide on here anywhere. I see it in the book down here. But that's bizarre. So we'll start there. Okay. Just need to do it. Okay, now let's do homework assignment for this section. And this is page 726. Do any of the odds 5 through 13. They're all at Calc Chat. 7's at Calc View. Do any of the odds 15 to 23. They're all at Calc Chat. 17's at Calc View. Do any of the odds 25 through 33, they're all at Calc Chat. 31's at Calc View. Do any of the odds 35 to 43, they're all at Calc Chat. 37's at Calc View. And then maybe we haven't done enough to do 45, so you can stop at 43 and we'll pick up and go from there. All right, any questions? Good deal. All right, that's it for today. That's it for this week. Be working on those papers. Be working on those tests. Try to get stuff into me next week so it's not all piled up on you during finals. Because guess what? I'm going to say it again. I'll give you your final exam on Monday. You got to get it back to me Tuesday, Wednesday, or Thursday. I'm not going to be here on Friday. I'm not even sure the school is open on Friday, but if it is, you could come and slide it under my door. Does everybody know where the office is? 265. Not that door here, but 265. You could do that if school's open, but it may not be open. I don't know if they're opening back Friday or not. It may be. I can't remember. They did strange things this summer. But I need it first thing Monday morning. If you do get it back to me, I need it first thing Monday morning. Okay? I'd rather have it Tuesday, Wednesday, or Thursday. So don't be having your paper still hanging over you or one of the other two tests still hanging over you. You need that whole time to work on that final exam. So get the others into me by Monday of the following week. Not this coming Monday, but the next one. And that way when I give you your final, you have time to do it. Okay?